In this video, we're going to learn how to actually take names and give appropriate formulas for binary compounds and specifically binary ionic compounds. Now, depending on where you are in your chemistry lessons, you may have learned that ionic compounds are often when you have a metal and a non-metal bonded together. So just a little quick review. Remember, everything on the left side of the periodic table is metals. Everything on the top right is non-metals, with the addition, of course, of hydrogen. And then the stairway is what separates metals from nonmetals. And there are six main ones there, boron, silicon, germanium, arsenic, antimony, and tellurium. Those are the main ones. So basically everything over here is nonmetal, everything here is metal. So if I have something that's metallic or a metal bonded with a nonmetal, we usually have ions, meaning one element has gained an electron and become negative, one electron has lost the electron, become positive, and in the process you have opposites attracting to form an ionic bond. And so we're going to need to use the periodic table, and we're going to need to use the numbers that are in the top right of each box, which are the oxidation states or oxidation numbers, and they really relate to how many electrons have been gained or lost in the process. So for example, if we look at aluminum, bring this a little closer here. If we look at aluminum, aluminum has a +3 value. That means that it's lost or can lose up to 3 electrons. When you lose 3 electrons, now you have 3 more protons, therefore you're +3. For example, if we go all the way over to magnesium, magnesium can lose 2 electrons. And a lot of that, I know this is hard to read, but if you look at the configuration 282, they often want to get rid of their outer electrons so that they can complete that inner shell for an octet of 8. And so on the opposite end, those nonmetals that are also very reactive, for example, chlorine has 7 electrons. It wants 1 more to make 8. So therefore we see a -1 on the top. All of the halogens have -1 at the very top of their configurations. Just like our group here, oxygen has 6 valence electrons, wants 2 more. So when it gains 2 electrons, it's now -2. As very similarly, anything else in the group, they all have -2 at the top. So again, what we're going to need the symbols, and we're going to need the values at the top, and we're going to do what's called the crisscross method when we're naming these binary ionic compounds. And again, if you think about crisscross, you're in elementary school or you're sitting down in kindergarten, you're crossing your legs. So the crisscross method, I'll just put it here at the top. So the crisscross method is what we are going to focus on. And I apologize for the shaking. I got my setup here and my phone's just sitting there videoing this, and it's a little wobbly. So the crisscross method, we are basically going to cross our numbers. Okay, we're just going to crisscross them. And what we need to do is look up our symbols, and we need to look up the numbers that go with them. We also need to remember when we do these, if you notice sodium, silver, aluminum, calcium, nickel 3, we'll talk about Roman numerals here in a little bit too, versus nickel 2. We got iron 2, we got tin 2, mercury 2, aluminum, calcium. The metal, the first word is usually the metal. That's our positive cation. The name stays the same. The second word, though, you notice bromide, oxide, hydride, nitride, fluoride, chloride, sulfide. These are all my nonmetals. So my nonmetal comes second. So metal comes first. That's the positive piece. The nonmetal comes second. That's the negative piece. The negative ion is called your anion. And so when we look these up, we need to remember that bromide really comes from bromine, oxide is from oxygen, hydride is from hydrogen, nitride is from nitrogen. You'll become familiar as you go more in depth with this, but just keep in mind it's not the name of the actual element. The ending has been changed. But I know that I need sodium, so Na, and I need bromine, Br. So I have to look up what the charges on sodium and bromine are. So this is where the periodic table comes into play. So when we look at sodium, sodium of course has a +1 value. And if we go over and find bromine, what we're going to use for the second element, we're typically always going to use the top number. And so in this case, bromine would be -1. And we'll talk about different exceptions, and I hinted at that a minute ago with the Roman numerals. But for the second element, it's pretty much safe to go with with the top number unless you've been told otherwise. So if I know sodium is a +1 and I know bromine is a -1, when I cross those numbers, nothing really happens. That's pretty straightforward. We get NaBr as my final product. I don't have anything there that really makes a difference. And so the other way that we could look at it, we could see if they are the same, they basically cancel each other out. Because when you have formulas, what you really need, if the whole thing is done, you need to have balance, you need to have neutrality. If you don't have neutrality, then you haven't had the correct formula. So let's look at silver oxide. We know silver is Ag, and we know oxygen, of course, is O. And so when we look up Ag and O, silver has a +1, oxygen has a -2. Okay, so when we take those numbers, silver is +1 and oxygen is -2. And hopefully you'll be able to see this because, again, I can zoom in on one but not as easy on the other, just because I have to write. When I take those numbers and cross them, okay, I'm going to bring the 1 down and the 2 over. We don't bring charge over, we only bring numbers over. What I end up with is Ag2O. And I don't have to write the 1. If you want to write the 1 here, you can, but you don't have to. Just like in math class, you wouldn't write 1x, you would just write x. So I don't have to write Ag2O1, I can just do Ag2. Ag2O, excuse me. And so then it is done. If we think about aluminum oxide, aluminum is Al and oxygen again is O. When we look at our aluminum, we mentioned aluminum before. Aluminum has a +3. Oxygen again is -2. So we have our +3, +3 and -2. Again, we are crossing the numbers. So my number comes down and my number crisscrosses over here. So I get Al2O3. And so we end up with a balanced equation overall for a balanced formula. Not necessarily a full equation, but a balanced formula. Now, what we have to think about this is that if we think about aluminum, aluminum has a +3 charge. So every aluminum is +3. If I have 2 of them, that really means I have a +6 charge. Okay, +3 and +3 is +6. If my oxygen is -2, but if I have 3 of them at -2, that's really -2, -2, -2. That makes -6. So I'm going to have +6 here, and I'm going to have -6 here. Those cancel out. And so at the end, when you make sure you're looking at your values, you want to make sure that you have your numbers correctly. Now, I'm going to just skip a little space here just because it's starting to get a little congested. But let's look at this second one. Whether we're looking at nickel 2 or nickel 3, we really need to make sure what we're doing. So I know that nickel is Ni, and when I go and find nickel on the periodic table, we can see that nickel actually has a couple options. It has +2 and +3, and that's where the Roman numerals come into play. The Roman numeral tells you what number you're actually going to use. The Roman numeral 2 means a +2. Roman numeral 3 means a +3. If you have a Roman numeral 4, for example, like palladium, you'd use a +4. If we go over to manganese, for example, notice we have +2, +3, +4, +7. We would see Roman numeral 2, Roman numeral 3, Roman numeral 4, Roman numeral 7. So you need to become familiar with your Roman numerals again. And so just as a little quick reminder, remember Roman numeral 1 looks like an I, Roman numeral 2 looks like II, 3 would be Roman numeral 3, IV is 4, V is 5, VI is 6, VII is 7, VIII is 8. We really don't go up above that. Just for the sake of what we're doing, IX is 9 and X would be 10, just in case you're coming across those. But really, this would be the highest one we see, with the manganese, for example, up to 7. A lot of 1s and 2s, 2s and 4s, things like that. So when I see this, for example, is either nickel 2 or nickel 3, that's telling me what I'm using. So we're going to do this one right here. We're going to do the nickel 2 nitride. So I know I'm using Roman numeral 2. That means I'm going to use a +2. Okay, the Roman numeral tells you the charge you're going to use. When we look at nitrogen for nitride, notice nitrogen has a ton of examples here. And so again, we're going to stick with the very top one, unless you're told otherwise. So we're going to start with the top one. So Ni2, and then my nitrogen is -3. We're going to crisscross our numbers, and I'm going to get Ni3N2. Okay, Ni3N2. Now, as we continue, a lot of times we're seeing that they're different numbers, and so this makes sense. It's pretty easy, pretty straightforward. But let's take a look at this one. Lead 2 sulfide. Lead 2 Pb and we're going to use the Roman numeral 2. Now, I don't even have to look it up on the chart. I already know what the charge is because it shows me a 2. But just to verify, if we go and find lead on our reference table, lead, of course, is Pb. And so over here, we have two options, +2 and +4. But because I'm using the +2 Roman numeral, I'm going to use +2. Sulfide comes from sulfur. Sulfur, just like oxygen, in the same group, is going to have very similar, an identical outside structure of 6 valence electrons. So it's going to gain 2 electrons in this case and end up with a -2 charge. And so sulfur is -2. Now, just like the sodium bromide we did up above, +1 and -1 cancel out. +2 and -2 are going to cancel out. So you can either do nothing and just basically cancel them out and say PbS, or if you really want to go through the steps, you could go through and say PB2S2, but then those reduce. You do have to reduce them, you do have to cancel them out, and eventually we come back to PbS again. So if you see things that you can actually crisscross and reduce, you need to go forth and actually crisscross and reduce them, because you want to have the lowest reduced value when you go through your examples, unless you have specific cases. Now, there are some specific cases, and mercury is one that has another example. When we get to table E, we're going to see something called dimercury. And there's different scenarios where you would actually leave the number and not reduce. But for the most point, for the example we're doing today, for your simple 2-element, that's what it means to be binary. Okay, binary is 2. So 2-element materials, they're typically just going to be able to crisscross and then reduce as necessary. Again, if it's the same number, they will cancel out. If it's a different number, then of course you are going to put both of those numbers down. They just switch. Again, we don't bring charges down, we just bring numbers down. And if there's a 1, you don't have to write the 1, okay? If we look at, for example, I know we're getting kind of close here with the spacing, but if we look at this one, iron 3 oxide, I know iron, Fe +3. We know oxygen, we've seen it already a couple times, -2. When we crisscross those, it becomes Fe2O3. Okay, that's Fe2O3. Now, if I had done iron 2 oxide instead, if we had Fe +2 and O -2, then those cancel out. They're the same value, equal and opposite charge, so they basically cancel out. We end up with FeO instead. Those two materials have a different formula, therefore they're going to have different properties, they're going to have slightly different chemical reactivity. So it's very important that you do pay attention in the lab setting. Now, when you're looking at it from a stockroom perspective, if you go into a lab, for example, and you say, oh, I need the iron oxide, the question is, which iron oxide do you need? Do you need the iron 2 or the iron 3? It might look a little bit different in color, maybe in structure, and definitely could have some differences in chemical reactivity. So there's something called the stock system as well, and that's where this really comes into play. The stock system deals with these numbers because there are slightly different variations between iron 2 oxide and iron 3 oxide, or for example, if I had nickel 2 bromide and nickel 3 bromide, nickel 2 nitride, nickel 3, okay, they all can be slightly different. So again, there is your breakdown for how to do the crisscross method with binary compounds. Again, so these are both elements that are coming off of the periodic table, individual elements. In another video, we will learn how to do crossing with larger compounds that deal with polyatomic ions, for example, or 3 or more elements, and again, dealing with things like table E. So look forward to the next video where you can learn a little bit more, and hopefully you found some benefit from this to help you go through your periodic table and to answer and to name your compounds.